Alright, welcome to video 8. We're now talking about dipole-dipole forces and hydrogen bonding, basically finishing up our kind of intermolecular force summary, if you will. The presence of a permanent dipole in polar molecules is what causes dipole-dipole forces. We talked about London dispersion, a temporary dipole, but when electrons are kind of occasionally just all on one side. However, in polar covalent molecules, we can either draw them like this, or sometimes I've seen like this, but we have a partial negative charge and a partial positive, which is basically where the attraction of ionic bonds come from. It's the negative charge attracted to the positive charge. However, we're not quite that strong, but we have at least a partial negative charge. So that is what causes the dipole-dipole forces. This negative end is attracted to the positive end, etc. These forces arise from our electrostatic attractions between, again, as I just said, the partially positive end of one molecule and the partially negative end of another nearby molecule. Keep in mind, we're talking about the same thing, because this is water attracted to water, for example. But we have the positive ends attracted to the negative ends. Dipole-dipole forces are also, as with dispersion, really only significantly effective when the molecules are very close to each other. The reason I put very this time as opposed to last time, I didn't do that intentionally. I don't want to throw you. These just really are over close distances. They're not as strong as ionic bonds. They've got to be pretty darn close to each other. Now these forces are, again, typically weaker than ionic forces or even actual covalent bonds because we're holding molecules to molecules. They're not bonded together and forming bigger molecules. They're just light attractions that keep the molecules somewhat close together. So just keep that in mind that intermolecular forces are weaker than almost any type of actual bond. But these especially are actually at least stronger than dispersion forces, so there's something. So since dipoles have both positive and negative ends, both attractive and repulsive forces exist. Meaning positive to positive, yeah, we got repulsive. Negative near negative, repulsive. Positive near negative, attractive. That's all Coulomb's law. And kind of common sense, to be honest. In solids, like ice, the molecules end up being arranged to maximize these attractive forces while minimizing the repulsive forces. It's actually kind of cool. You end up having this kind of little layered structure, if you will, where the red represents either positive or negative and blue represents the other. It doesn't really matter. But these are attracted to each other, but the blues try to stay away from blues and reds try to stay away from reds. It's kind of cool. So this way you've got really high attractive forces and pretty low repulsive forces. Now, I know this is just a two-dimensional model. Three-dimensional basically still tries to work on the same concept. It's just a little bit harder to draw. In liquids, though, these molecules are free to move around each other. So they still form a similar type structure, but they can move around a little bit, and 3 dimensions get a little bit kind of easier at times. But you're still trying to maximize attractive and minimize repulsive. For molecules of about the same size and mass, the strength of our dipole-dipole forces increases, like with dispersion, with increasing polarity and polarizability. So the more polar the molecule, the stronger the force, and the more electrons, the stronger the force. Hydrogen bonds, though, are a special type of dipole-dipole forces. These occur when, in addition to our existing dispersion, remember I said everything has that, and dipole-dipole, the hydrogens are also attracted to nearby really highly electronegative atoms. That's why we typically do nitrogen, oxygen, and fluorine. So you've got kind of the secondary attraction, if you will. Typically represented in diagrams as dotted lines between hydrogen and either nitrogen, oxygen, or fluorine. Just whenever you see hydrogen in a dotted line, that's probably a hydrogen bond going. And again, they're not full bonds. That's the thing you got to remember. It's not a bond between... Here, let me just show you. So this is a covalent bond. These are covalent bonds. This is hydrogen bond. So that's really what we're talking about. It's not actual bond. It's just the hydrogens being attracted to them. So you've got the positive end and negative end attractions going on, and the hydrogen bond attraction going on. So these end up being actually significantly strong. These actually explain a lot of the properties of water we know about, and many other polar covalent molecules with hydrogen and nitrogen, oxygen, or fluorine. But they can get pretty strong. Our next slide does actually, in your notes, have an example. I apologize. It doesn't really deal with what we're talking about, at least not the way I've been showing you. We'll come back to that maybe a bit later, but for now, I'm not going to use that example. Just knowing really what they are, where they occur with, that they're stronger than dispersion and dipole, that's really all you need to get. So with that, again, not doing the next slide, thanks for watching.